Good morning, everyone. We are glad and proud to present you a work of research, but also, and above all, of pedagogy on the specific typology of elastic post-form gridshells. This work has been performed for a full-scale public pavilion called Elastica in collaboration with the Paris City Hall and the 19th District City Hall by the students and teachers of School of Architecture of Paris.
Let's start with the definition. So what is an elastic grid shell? In architecture, a shell is a continuous thin structure with a curved surface. Its rigidity is related to its curvature. Then a grid shell is a structural lattice of bars forming a curved surface. Laby classifies grid shells into two main groups: those with pre-calculated members, both in their curvature and in their geometrical resolution, but also in their inactive bending fixings, and those known as active bending, which start from an initially flat grid, which connections are not fixed until after their assembling, once the structure is established in its architectural form. The elements of the last category, called elastic grid shells, are working in flexion and compression. It was not until 1962 that this typology was highlighted by the work of Fry Otto. He had been carrying out studies in the late 1950s on the lightweight shells from suspended net models, and built a first trial model of an elastic grid shell during a visit to the University of Berkeley. Designing an elastic grid shell requires a good understanding of bending. To understand an elastic grid shell, it is fundamental to question the natural shape of the flexible rod in pure flexion. In the framework of classical beam theory, bending moments induce deflection and not the opposite, which implies that the supports, including the sliding supports, remain immobile on the drawing. This theory is therefore valid only for small deflections and rotations, where this inconsistency is considered insignificant. In fact, when the initially flat grid is shaped by the bending resulting from its buckling, the hypothesis of small displacements and fixed supports is fundamentally questioned, since it is precisely the displacement of the mesh supports that will give the shape of the grid shell. Form finding can be carried out either experimentally, by means of hanging chain nets or active bending models, or numerically, for example through dynamic relaxation. The work of Fry Otto, Arup and Helmut and Little has been tested by all three methods and provides valuable data for assessing the relevance of each. The use of the hanging chain nets model can be surprising, since the notion of an anti-funicular and therefore pure compression is used to model an object in flexion and compression. To confirm its relevance, in 1973, Linkwitz digitally modeled the Mannheim model using the photogrammetry. The calculations conducted by Hubble took into account the bending and led to results similar to those of the hanging chain nets. About the active bending model, in 1963, Apple's team studied a simpler example by loading a PMA model of the trial gridshell in Essen and comparing the results with the data collected by the Wormbrome workshop on the actual project. The team found and retained for the Mannheim project that the addition of bracing on the diagonals of the layers reduced deflection and increased the maximal nodal load, causing buckling of the shell, but that the collapse was more sudden. To overcome the inaccuracies of form finding with the model, a numerical method is generally necessary. The shape resulting from the initial phase of intention, which we will now call architect's shape, is not the real shape of the project, which must respect the rules of physics, especially bending. The form finding consists in determining from the architect's shape what the real shape is going to be. The first step consists in dividing the architect's shape into a network of two layers of bars forming equilateral meshes. That is a necessary condition for flat fabrication. The division of any surface into equilateral parallelograms is called a Chebyshev lattice.
This form-finding method, even though simple since it's based on the law of Newtonian physics, is iterative and heavy by its quantity of calculations. Its development had to wait until the end of the 20th century and computer-assisted numerical modeling. Dynamic relaxations allows to solve static equilibrium problems by a fictitious dynamic calculation. It is valid for large deflections. The architect's shape is not the natural form of the project, so it is not at rest. It wants to move to its natural position. It needs to relax. Thus, the fictitious motion of a structure modeled by a discrete mesh of bars at the intersection of which are locating the nodes, subjected to forces, must be calculated. Indeed, according to Newton's second law, the sum of forces is equal to the mass multiplied by the acceleration. If the forces at each node do not balance, then the nodes experience a fictitious acceleration and therefore move at a velocity that varies with time. This let us calculate at each iteration the position of each node at the next instant. In the case of a gridshell, there are at least three forces acting at each node. The nodal net weight, the force induced by the bending of the elements, and the hook force in each element. Once the acceleration at the fictitious instant t has been calculated and knowing the initial velocities at the same instant, we deduce nodal velocities at the following instant and then the displacement by a kind of integration. We then obtain the positions of each node at the time t plus delta t. The operation is repeated until an equilibrium of forces is reached at each node. The structure is then at its natural position.
At the initial instant, the deviation between the initial arctic shape and the equilibrium shape being maximum, the potential energy related to the forces resulting from deviation between the considered position and the equilibrium position of the system is maximum. The initial node of velocities is being zero. The kinetic energy of the system is as well. The relaxation then causes the nodes to move. The equilibrium position is obtained when the potential energy is zero and the kinetic energy is zero. The nodes no longer move. In the intermediate stages, energy transfer takes place between potential and kinetic energies. When the system passes through its equilibrium position, the forces balance and the potential energy becomes zero. But nodal velocities, which is then maximum, causes the continuation of the movement in the opposite direction. The system oscillates. The fictitious oscillation around the equilibrium position will be endless without the addition of damping, a way to fully dissipate the total energy of the system. This algorithm is the concrete application of the principles that we have presented. It is usable for any type of elastic gridshell and available in open source on our website. We can now present a physical application of this Elastica algorithm. The Elastica project has been designed after various tests comparing numerical and model status. Let's recall that surface buckling is the main cause of failure of an elastic gridshell. According to Happel and Little, all other things being equal, the use of bracing and double lathing increases the critical load by a factor of between 1.60 and 4.44. Furthermore, we can predict that the addition of shear blocks will increase the critical buckling load by a factor of about 13, determined by the ratio of inertia with and without these blocks. The results of our modeling of the Elastica project confirms the predictions. Our results of the three designs tested confirm also do theory for whom critical load of a grid shell is close to that of an equivalent cylindrical shell subjected to hydrostatic loading. The results of our study showed that the expected loads of the Elastica grid shell require a double lap design with bracing and shear blocks. Stress in timber elements are due to its bending during the assembly phase and then, in the service phase, to the self-weight and variable loads. However, shear blocks are added after erection, increasing the inertia of the members by 13 in service phase. In addition, during the erection stage, the laths work independently, while in the service phase, double lathing works as a single Girondel truss. We have therefore simulated and combined three stress cartographies to obtain the resulting stresses in turbo elements in service stage. Elastica algorithm is also able to conduce steel bracing verification and to give the horizontal reaction at the basis of the grid shell.
We would like to conclude this presentation by thanking all the students who have taken part in and all our partners who have contributed to the success of this work.